Hello, this is Matthew O'Brien, and I've got a really good treat for you this time. I've got a video on how the coronavirus would spread in 2 dimensions, 3 dimensions, and 4 dimensions. What does that even mean? I will show you. I've got animations. I've got this particle simulators where particles are moving around spreading the virus. You may have seen something like this in 2D, but then I'll show you in 3D and 4D. And I'll even take you up to 20 dimensions. And that's going to be crazy. And I got some really cool results to show in higher dimensions that I was surprised by. I had this general tool, so I said, okay, let me play with it. Let me see what happens. And it's really cool. Let's take a look. The red particles are infected, and if they bump into a green particle, which is healthy, they infect it. They turn it red. And over on the right here, we're watching the number of infected particles. We see it grow up, grow. And then after 2 days, the infected particles turn blue. So we see some blue guys turning up that are healing. After 2 days, they heal. Now it looks like everybody's... Oh, I see one holdout, one green guy. And the infection is wearing off. And everybody eventually will heal and turn blue. So now let's look at social distancing. Let's say 50% of them don't move. So in this case, 50% of them aren't moving, and the red guys are infected. They're moving around, infecting the green guys, and then after 2 days, they will turn blue. That means they've recovered. So here, this kind of flattens the curve a little bit with 50% social distancing. It doesn't go up quite as high. And then after enough time, everybody heals. Looks like there's some green guys that didn't get infected. Now let's look at 85% social distancing. So only 15% of them are moving. So now this really flattens the curve. It spreads much slower. So perhaps this is the state we're in now, where most of us are social distancing. So we've really flattened the curve. We see it doesn't go up very high. It peaks at around 50. There's 200 particles in each of these simulations. And this one, 85% of them are not moving. So the red guys are infected, the green people are healthy, and the blue people have recovered. So now let's look at this in 1D. The red particles are the infected, and we just kind of see it spreading out on the left. And there's no way for them to avoid it. They can't move around each other, so it spreads really fast. Everyone's going to get infected. And 1D, there's just not enough space to move around each other. And so we just see everyone gets infected, it maxes out, and then we fast forward ahead, and then eventually people recover. But what about 3D? In 3D, it's the opposite. You have more space. So now the red guy's infected, and he's hardly colliding with anyone. There's just so much space in there. It's the same 200 people. The size of the square is 1 by 1 by 1. And look at this. Hardly anybody gets infected. On the left, the curve is really flattened because there's just so much space. Our goal is to get to a 4-dimensional visualization, but we're going to work our way up to it. We're going to start with a 3-dimensional visualization as 9 2-dimensional visualizations. So on the right, we have these different colored balls. We've got the yellow ones on the top, the black ones, pink, brown, purple, red, green, orange, blue. So each of those little strips in 3D gets mapped over here to 2D on the left. So 9 2D drawings is sort of approximating that 3D drawing. That's the idea in this thing. So as particles stay in sort of the plane, they'll stay in one of the 9 drawings, but then as they move up and down, they'll change into which 2D image they're in. Let's keep our attention on the red dot in the center pane. The red dot's going to move to the left pane. It's moving down in the Z direction. See, there they are and they keep moving to the left panes. Now they're going to reflect and start moving to the right, and eventually they'll heal and turn blue. Now let's look at the 4-dimensional visualization. In 3 dimensions, we saw we could take a thin strip of 3D and make it 2D, so we're going to do the same thing in 4D. We're going to take 9 thin strips in 4 dimensions and make 9 three-dimensional plots. So each one of these 9 panes is a thin strip in the 4th dimension. So if the particles move, look at this red particle on the left here. As it moves in the same XYZ space, it will stay in that pane, but then as it moves in the 4th dimension, we'll see it jump panes. So let's watch what happens. Let's watch the red particle. Oh, it's moving to the right, which means it's moving in the positive 4th dimension. It's moving to the right. Notice how it's not, now it's going to eventually reflect. It has a reflecting boundary condition and start moving back to the left. So, and now it healed. Blue means healed. So in 4D, there's just a lot of space. You can not only dodge in 3 dimensions, you can also jump into another completely disjoint 3D world, so to speak. Now let's see what happens when we increase the size of the spheres. Of course, the virus is going to spread faster because they're going to the particles are going to bump into each other more quickly. Let's watch what happens. Very quickly it spreads. Jumps way up so that everybody's infected pretty quickly, and then it dies away. Now let's make them even bigger. Now it spread really fast. So we see this top hat function. It jumps up really fast so everybody's infected, then falls back down. And so let's look at that in higher dimensions. Okay, this result blew my mind. We have a unit box. The size of each dimension is length 1 in the X, Y, Z dimension, in every dimension as we keep going up. So what I'm going to do now is I'm going to make the balls have radius 1. So in low dimensions, the balls are completely filling the box. And we're going to see this top hat kind of feature where they infect everybody right away, wait for 2 days, and then everybody heals. So let's look at this, what happens in up to 10 dimensions. So now I've plotted this in the first 10 dimensions. We see everybody infects each other almost instantaneously. All 200 people are infected. We wait for 2 days and everybody heals. But, okay, that was up to 10 dimensions. Does this hold for every dimension? Let's keep going. Let's put up to 20 dimensions on there. So I reran the simulation up to 20 dimensions. Now, holy smokes. What this is saying is that in these higher dimensions, I've got unit spheres, a sphere of radius 1, and in 20 dimensions is this like kind of turquoise curve way on the bottom, way near 0. The spheres are almost completely avoiding each other. So moving to a higher dimensional universe is a very good way for avoiding the spread of a virus, but it's difficult for us to do that. I don't know how to do it. And let's count up this. We have this turquoise one, then this greenish one, then this grayish one is 18 dimensions. That one kind of has some very interesting behavior. So what that's saying is you have a sphere of radius 1 inside an 8-dimensional box where each edge of the box just has length of 1. So in low dimensions, the balls are all crowding each other out and overlapping, but in high dimensions, this is not the case. So let's take a look why. Let's look at the volume of an n-dimensional unit sphere. A unit sphere means the radius is 1. So a 0-dimensional unit sphere, by definition, has volume 1. A unit sphere in 1 dimension is a line segment where the points are distance at most 1 away from you, so that it's a line segment of length 2. And then we have this really cool recursive formula. The volume of the nth unit sphere is 2 pi over n times the volume of the guy 2 dimensions below. So this factor 2 pi over n is going to be less than 1 when n is sufficiently large, like around 7. And then, so what that means is these start decaying away very faster than exponential decay. It just keeps getting smaller and smaller and smaller very, very quickly. So let's look at a graph of the volume of an n-dimensional unit sphere as a function of n. It has this nice, beautiful curve to it. It peaks out at 5. That's the largest volume unit sphere is in 5 dimensions, and then it decreases after that. if we plot this on a log scale, we'll see how quickly this thing decreases. Now let's look at the volume of an n-dimensional unit sphere on a log scale. So I'm going out to 200 dimensions, and we can see these volumes get tiny. At 200 dimensions, it's 10 to the minus 99. That's 0.00000 with 99 zeros, 1. It's this tiny, tiny value. So now we can start to begin to understand why the virus spread so slowly in higher dimensions, because these volumes keep getting smaller and smaller. So our intuition about what a radius 1 sphere is in higher dimensions just goes away. It's this tiny, tiny thing in higher dimensions. We learned some crazy things. In order to visualize 4 dimensions, we can take a thin slice of 4 dimensions, and that's 3-dimensional. So we take a bunch of these thin slices in 4 dimensions, and we get a bunch of 3-dimensional plots, and we can see particles moving around in the 3-dimensional world, and they can also jump plots. So moving in the 4th dimension is kind of like jumping to a completely different 3-dimensional world. We also saw that I can take a unit sphere and put 200 unit spheres in a unit box where the size of the length of the edge of in every dimension is 1, and up to 10 dimensions, these things are all crowding each other out. They all collide with each other right away. Everybody's infected. 2 days later, everybody heals. But as you keep increasing the dimension up to 20 dimensions we looked at, eventually there's so much space in there that these things are actually missing each other. These spheres aren't even intersecting, which is crazy to think about. And we saw the volume of an n-dimensional sphere decreases faster than exponentially. So these things are these tiny, tiny things that just don't intersect each other, just somehow miss each other in these high-dimensional spaces. And I thought that was really cool. It's crazy. And if you are a good artist or an animator and you would like to work with me, or actually if you're good at anything at all and you want to collaborate on a video, please let me know. And if you're still watching at this late into the video, that means that you really like this kind of stuff. So please tell other people about it. I would like to thank my friend Britton and his son Will, who's in 5th grade, for writing the 2-dimensional version of the coronavirus simulator, and then I extended it to higher dimensions. Thanks, guys.